Thank you, Tom, for inviting me to this meeting. So, Sören Knuts is my name, and this is the agenda for this talk. I will briefly just present myself, and then GKN Aerospace, and then I will bring this a bit more back to basics regarding robust design and the robust design issue and identification of sources of variation, and then I will also discuss our business where we see that we are creating a robust business through unrobustness. And I will tell you more about what that means for us. And then we have the Six Sigma into solving or resolving our robustness problems. And then we see the GKN Robust Design that includes key characteristics identification, but it also includes geometry assurance process. So just briefly regarding myself, and I wanted just to put a stamp on Niels Bohr up here, and there starts the Copenhagen School about 100 years ago, and I was myself into quantum physics once in a time, about 20 years ago, but then I switched business. But there you see my interest in science. But then I came to Trollhättan. I started with space propulsion, and there I also got very interested in quality issues and reliability. And then after being quite deeply involved in the development of the Ariane nozzles, Ariane 5 nozzles, I continued to Saab Automobile that was also in Trollhättan. And there I continued with working with risk analysis, FMEA, statistical analysis, and there I started also with design for Six Sigma. And then I went back to Volvo Aero, where I started in Trollhättan, and continued more or less with the same thing. And then I got to be their specialist in design for robustness. And now we are GKN Aerospace since 3 years back, a British company that I will next talk about, but I regularly are running master thesis works and student projects in robust design and Six Sigma. And then I have also participated quite a bit in a European network in business and industrial statistics and this. And there I have met a lot of people from Novo Nordic, so I know they have a lot of good statisticians. So, GKN, engineering that moves the world. And here you can see that there is a great variety of businesses that we have, where aerospace is one business, and we are supplier to bigger companies. I guess Jaguar Land Rover is one, and Volvo is another one, I know. And if we go to the GKN Aerospace, making things fly, we see that there we also have a great variety of different businesses. And I will mostly focus here on the commercial aircraft engine side. But there we also have the military aircraft, and we have space launchers for Ariane, for instance, and engine services. And we are about 12,000 employees, and in Trollhättan we are about 2,000 people. And here you can see one of these commercial engines, and we have specialized in having two parts of structures, one on the cold side, where we have the fan static part, and one on the hot side, where we have the turbine static part. So we do not have the moving parts. So we have some moving parts, but these are the structures we have specialized on and made a very good business on, where we have more or less 90% of all the large commercial aircraft engines. So when you are flying, you certainly are flying with components from GKN Aerospace. And then you want it to be very reliable, of course. So reliability is a big issue, of course, but robustness, that's where we are going to earn our money. And here you can see the hot topics within GKN Research and Technology, and there you can see that 3D metal printing, or building up parts by additive layers of metals, where we are mostly welding. That is one important technology that we are building up. And we have the automized welding, welding with lasers. That is also very important technology we are building up. And then finally, we have the lighter structures and introducing composite materials in engines. And so far, I don't think there are so much composite materials in aircraft engines, but they are on the way. They have not yet been matured enough. So what is the robust design issue? The main issue, and I think that was touched very much yesterday in the doctoral thesis, Martin. And this is very much what we have been trying to develop here for the last 7-8 years. Can we design our products and processes so they are insensitive to sources of variation? But here it's very much to understand what does it mean for us in the type of business we are in. Because it's not the automotive industry. Here we have an industry where we have much fewer parts. It's not consumer parts in the same sense. But also the high requirements we have in our business also put a lot of constraints on what we can do. And if we look into this classical bathtub curve, we have divided it into 3 phases. And the first phase here we call a robustness phase. And the next phase we have reliability. And then in the last phase, the wear out phase, there we are not operating. So what we are determining there is rather to estimate the life of the parts. So we have margins. And a lot of focus is put on the reliability part, but when it comes to earn money and create good conditions for our products, the robustness phase is what we have to focus on. And that is also, I have been very much focused earlier on reliability, but I have to shift here. And there you can see typical noise factors related to these different phases, and manufacturing imperfections. That's really what we aim for when we are discussing robustness. And the other noise factors you can recognize for typical consumer products regarding external environmental load conditions. Customer behavior. So we continue with manufacturing imperfections. So when we work on identifying these sources of variation, we see the type of problem that Martin was facing yesterday in his dissertation thesis was very much how can this be applicable in a simple way for the engineer. And what we can see here is that in our organization, we can talk about these tools, but what the engineer is doing is that he is using FMEA, but in his FMEA, he's not addressing the sources of variation. There we have the problems. We see when we work with root cause analysis that these fishbone diagrams or Ishikawa diagrams are very fruitful in order to mapping out different factors. And what I have used here is really a P diagram, and I think that's a good way of understanding what type of problem you really are facing, that you have to differ the different factors that you have in your engineering problem that you have to solve, and you really have to understand the problem, the system you are studying. And then the question is very much, you have these control noise factors, but you also can talk about quality parameters or characteristics related to solving this problem for both hardware and the industrial process. So you have to connect these two. So the GKN design problem is very much this problem, to find the key product design and process parameters, but then also to understand the voice of the process. And there I would say we have the noise factor that we have to get more and more aware of. There we have the tolerances that the process is creating. The tolerances that we are setting in design is not always connected to what the actual process says. We have some big issues there to work with. So, how are we then creating a robust business on our products? We are actually creating unrobustness. And why are we doing that? That's kind of a strange thing, and I have got comments on that before. How are you thinking? You should do robust design, and now you make things unrobust. But that's a competitive thing. Because what we want is to go from these unit or one-piece casting that is very heavy and big to smaller pieces that we can control the weight on and get to a much more lighter fabrication. And from this we can talk about make it light. And there starts our travel. We should provide light structures for our OEMs, our aircraft customers. So we have this Think Green initiative within GKN, and sustainability is one of these big issues concerning this. So what have we done? So what we are doing is actually that we are partition these big structures into much smaller parts. And by this we can divide the part in more the delicate material where we can have castings, we can have forgings, we can have sheet metals, we can control the way the dimensions are built up in this product. And that's the way that we have addressed the make it light problem. But what you can understand here is that this is really creating a lot of problems with all the degrees of freedom we get into solving this problem. And I would say that when you are comparing it with the car industry and how we are setting up our process, it's like backing the time 100 years. We have not that type of automated process, but we are heading for it, and now we have good ways of actually working with the data around the process. But what data should we work with? That is really the problem that we are facing. And to be honest here, so what we in a way want is to reach this type of tolerance limits 0.1 millimeters that we have in machining operation. And in machining operation, we can have these bigger castings. But now when we have these fabricated components, then we have larger uncertainties that we have to handle. So what type of unrobustness are we then facing when we are doing this fabrication? So what do we have to care about when we now are developing our structures? We have to care about geometry deviations, deformations, and mismatch. And that comes very much from how we assemble all these small parts. And then when we are welding, we get deformations from the heat up of the material. So how can we control this? We are very good at simulating even welding, but anyway, we are not precise in how this is done. So dimensions are important. In the welding, we get weld defects, cracks that we have to control. And we also have to show by inspection that we don't have defects in our welds. So it's very much how can we show that our processes are defect-free. And then it comes to the material that we are using. Castings have slightly worse quality than forgings, sheet metals. And then, of course, how are we controlling our process that we are applying, all the welding process parameters. And you can understand that this adds up to high lead times, high number of non-conformances that cost a lot of money for us. And we also have expensive rework when we have to do rework. So here it's very much to work with the manufacturing process at the same time that we have to work with the product. So here you can understand that we have gone very much from having no identification to now we are very much into identification phase, where we understand how different factors are varying together. But we have to go into processing control. We have to get a very accurate description of how we can get robust products and processes. And here we also see that the Six Sigma methodology has helped us very much in the way of thinking regarding the way we are working with production processes in order to get this optimization happening. And there I want to show you just briefly the DeMike process, which I think has some very good components that you have to get the engineer to understand when it comes to controlling the output of your process. And there I want to stress the aim, where you have to look at the problem. You have to question, have you defined your problem in a very good way so you can solve it? And what we mostly are seeing is that you have not looked through the context, made the analysis. You try to find the simple solutions to the type of problems you are seeing. And that is something that we see that we are questioning and working with in a very good way in this Six Sigma methodology. And then we also see that when it comes to working with measurements, we haven't really made our exercise concerning the measurement system analysis. And that is also something that we are working with to correct. And then, of course, to really study the process and study how the deviation looks. So we actually reduce the variation in a wished way. So I want to connect here to, and from the sense of measurability to actually a concept of key characteristics. And there we saw in the academic literature that this is a quantifiable feature of a product or its assemblies, parts or processes whose expected variation from target has an unexpected impact on the cost, performance, or safety of the product. And that's a reference to Anna Thornton, who is here today. I think this is a very fundamental work in variation risk management that really goes to the point with what is robust design. but it's very fundamental. So from that point of view, it's sometimes a bit hard to apply, a bit theoretical. And what we see from our customers, because the definition of key characteristics you have within the aerospace business. So this is something that we have in our aerospace standard. And you have more or less a definition that is very similar to what Anna Thornton put here, with the purpose of controlling variation. And where we put a lot of emphasis on producibility. But what we see when we are applying it, and we have made our own classification standard on this in order to really see that we understand the problem. But then our customers, they have also put their definitions. And here comes the problem, that when you do these interpretations, you are moving away from robust design. So when we try to work with these concepts, it's not always robustness you see when handling key characteristics. And that is something that I kind of fighting for in the organization in order to get some kind of mind shift on this concept, because it could be used in a better way for robust design purpose. And therefore, we have also proposed to have some kind of characteristic that we call actually a robustness characteristic that lifts the internal use and the internal need for actually measuring in production, to have good measurement data input when we are actually working with producibility issues. And there you can see on the drawings we have special ways of marking these characteristics in order to actually communicate from the drawing definition to our manufacturing organization on how to control this. So the three above we are speaking about, but we have a hard time with the key one. That's the one that is the problem. I would say safety and reliability characteristics, they are normally put out in a fairly good way, but the robustness thing is the critical, or the one that we have to work even more with. And here you can see a toolbox for investigating these robust design features or key characteristics. And there you can see a very varied toolbox with different tools, from statistics, design of experiments, historical data, risk analysis that can be used. And everything is about understanding the problem, the robust design problem. And I would say that that is also addressed within aerospace industry standard. So this is not something unique for us, but this is something that is addressed, but then we see that maybe it's not so well developed as you could think of, but that's where we want. And here we have one way of working with the identification, and in variation risk management, you see you need to have a risk thinking, and there we have our design FMICA, and we want to work with the design FMICA then as a tool in order to identify these parameters and characteristics. In different phases we have then different goals. And then the main principles here is that it should start with a large pool of key characteristics in an early phase, and then we actually work with eliminating these key characteristics and sensitivity by doing activities. And here it's very much how do we collect evidence that we do not have sensitivity. And then finally we should come to a few key characteristics. So am I a bit short of time here? Or so I speed up.
Maybe 5 minutes?
5 minutes, yeah. So I will make just some brief conclusions here. So here we have one picture on key characteristics, and there we have one sector, and you can understand that it's in this chain. And we have customer requirements put on it. And if we go down here to offset between parts, you can typically find these characteristics on such things. So here we have the offset on a drawing that could be put as a key characteristic. And first we have actually to put it potential in order to work with it and to get data. And here you can see other characteristics that is on the aerodynamic surfaces. And here it's really taken with a target system, this measurement. And then I want to move over to the geometry assurance process. And there we see that we have the RD&T as our tool. And there you can see these are typical the activities that are being run with the RD&T when we do work here. And also there we are finishing the loop with having Six Sigma work, a root cause analysis whenever we need to correct. And here we have an example where we have a Reengineering project where we have an old way of designing the way we are joining two sectors. And then we go to a new way of designing this. And there we also have to address what type of requirement do we have, key characteristics with weld offset. And here we are addressing, we are going from actually controlling the weld offsets by forces in a fixture. So there we build in tensions, stresses in our structure to a new way of controlling these interfaces by machined interfaces, since there we can very accurately control the dimensions. As I said 0.1 millimeter we can do with machining. So there we have an accurate process that we can use. And then here it shows some results from how we use geometrical optical measurements in order to measure on variations. And here we have actually used the RD&T software in order to simulate the variations and being able to compensate for the variation we have in the structure. And then here we actually do the compensation. So we build up materials in order to machine it later on and correct for the geometry. So what the GKN robust design process is making things insensitive to variation. And there we see typically a risk process with identification, assessment, and mitigation. But we also see the importance of addressing measurement system analysis and SPC. And then having this recovery whenever it's needed by being able of running root cause analysis, Six Sigma work. And there we have both key characteristics and geometry assurance involved. And that's what we are trying to implement in our system or work process. So thank you all for listening.
Two quick questions. I saw a lot of effort to handle existing design and avoiding problems here. I didn't see a lot of indication that you actually try to design in a way so that you will put all this out of work.
As I said, we are creating unrobustness. That's one of the problems. So now we have to take it back. We have to try to make the unrobustness robust.
How do you challenge the designer to make design solutions that doesn't really need a lot of what you did there?
I would say that what I showed here in the end, where we have actually recovery, we know our problems. I would say this fabrication method is only just a bit more than 10 years old. And from this, we haven't really collected so much experience and data. And that's what we are starting to get now. And then it gets more clear. And as I said, we are working much with the measurement systems to really get the right data out of the system. And there we have to mature the engineers in really questioning this, because they have taken so much for granted regarding how manufacturing is dealing with taking measurements and trying to fulfill really our needs. Or meeting. So here it's very much to work with problems, but also to be proactive for the next engineering loop of product. So we're actually building in these systems that makes it possible for us to recover in a good way and in a fast, efficient way. And that's really one of my message here, that think about the measurement systems where you can recover from having problems. So you more easily can make things more robust.
I'll take one more from Robert. Yes, Martin's PhD thesis yesterday, and also some of the parts from today has focused a lot on reducing overconstraints in your components. Do you believe that it's possible in something like an airplane engine to take away these overconstraints to actually reduce the number of needed measurements and tolerances and tight fits?
So I haven't made a big analysis here regarding overconstraints, but I see what the geometry assurance process does for our product is very much to give the engineer insights in how is variation affecting your product. So from my point of seeing there is rather to involve geometry assurance much earlier, and the way we are addressing target system, reference systems in how we are building up our product.
Okay, Sören, thank you very much for your interesting talk.
So thank you.